Okay, everybody, we're going to go ahead and get started. I want to welcome you to today's webinar presentation hosted by the IEEE Standards Association. My name is David Stankiewicz. I am the event producer for this session and your quote-unquote MC for today's webinar on the topic of IEEE Green ICT Initiative Standards. We are so very lucky to be joined today by Jafar El-Merghani. Jafar is from the University of Leeds in the UK. And we also have three surprise guests on the line as well, some other subject matter experts, if you will, in this space, who Jafar is going to introduce to us momentarily. Next slide, Jafar. And it's just a basic intro slide. I want to let everybody know before we get started, there's a few housekeeping items, and below are three different ways that you can participate in today's session. If you join today's webinar listening through your computer speaker system, also known as VoIP or voice over IP, this means you'll be able to hear the presentation in its entirety without dialing in using your telephone. So this is a one-way broadcast from myself, Jafar, and the three guest speakers to you. At the end of the presentation, though, we will be taking questions from you, the audience. So you have the ability to ask any of our guests a question using the WebEx chat feature. This is located in what should be the upper right-hand side of your WebEx interface or window pane. If you simply click that chat button and type your question in to the host, myself, David Stankiewicz, and click send, we will get to as many of those questions at the back of the presentation as possible. We're also recording today's webinar, so I want to let you know that the recording feature is on. If you come in late or you have to leave early, if for whatever reason anyone who's watching this on demand missed the entire session, you will be able to go back and watch it. We will be sharing out not only the recording of this presentation, but Jafar's PowerPoint slide deck as well. So Jafar, if you want to go to the next slide, I'll go ahead and mute my line, let you take us through the agenda, and if you want to unmute yourself, I will kick it over to you.
Welcome everybody, and to this webinar. I'm Jafar El-Merghani, as introduced by David, and this is our agenda. The welcome has already started. I'll in a short while introduce myself, but I'll also then be going on to present an overview of the IEEE Green ICT Initiative, the standards. And as David mentioned, we have three guest speakers today, and hopefully they will interact with you more during the question and answer session, Thomas, Anna, and Elle. And at the end, we will have a question and answer session just before the end. Okay. Right, so this is just a little bit about my background. I'm a professor in the University of Leeds in the School of Electronic and Electrical Engineering. My research is in communication networks and systems, and I have been co-chair of the Green ICT Initiative now for about 4 years. I have research in optical systems, but generally also in networks. I've published a number of papers, and I've been with the IEEE and the IEEE Communication Society now for roughly about 25 years. And over this time, I have chaired different committees and participated in the Communication Society in different ways. The initiative, I'll mention a little bit more about it as we get going, but it is a Pan-IEEE Society's initiative. Okay, so this is an outline of today's webinar. I'll start with an introduction, and hopefully here I'll say a little bit about the ICT carbon footprint and some of the traffic trends, and hence the motivation for establishing those standards. Then I'll talk about the IEEE Green ICT Initiative itself and what it aims to achieve and its areas of activity. And then the bulk of the presentation is going to be around those three areas, which are the three areas in which we have the standards. The first area is a set of standards for green core and content distribution networks and virtualization. I'll not go through them one by one, but there are 5 here, and we'll go through them as we go through the presentation. Then there is a second area, standards for energy efficient communication hardware. And this is, as can be seen clearly, is more focused on communication hardware. The first one is more on the network and the content distribution. And then the third one is more focused on emissions and estimation of emissions. And each of those two areas have got 2 standards. So in total, we have got 9 standards that have started as a result of work in this initiative. So making a start talking about ICT and its carbon footprint and some of the traffic trends. These are results that were shared with us by GESI, the Global E-Sustainability Initiative. And they show, first of all, here the carbon emissions worldwide. So for a long time, the largest amount of emissions used to come from the US. Until about just after the year 2000, China overtook that as the largest producer of carbon emissions, and these are quite large. So here is an example of telecom or the telecom industry. In Italy, for example, Telecom Italia produced about 1% of the emissions and used about 1% of the total energy in the country. And in many countries now, the telecom companies are the single largest consumer of energy, so way ahead of manufacturing industry, train companies, and so on. These are results as that were also given to us by Alcatel-Lucent, now Nokia, Bell Labs, as a result of engagement in Green Touch. Now, looking at how GESI broke down, the Global E-Sustainability Initiative broke down those emissions or those contributions by the different sectors of ICT. Telecom contributes about 25% of the total emissions, data centers about 18%, and the rest is preferred devices, about 57%. So these standards are mainly concerned with the telecom and the data centers part. ICT overall has got a carbon footprint that is comparable to the global aviation industry, which is quite huge, about 2% of the total carbon emissions in the world. And this is expected to grow to about 4% by the year 2020. And although it is large, the other thing that we have to remember is that ICT is growing at such an incredible rate compared, say, to global aviation, which is probably not growing as much or is almost flat. To understand what is driving this forward, we need to look at the traffic, and this is a set of traffic projections produced by Green Touch, and Green Touch is an organization made up of 50 member organizations, so it is an international consortium made up of industry and also universities. And roughly just at the turn of the century, traffic was growing roughly at the rate of about 300% per year. And obviously everybody expected it to grow even further, to grow like that. Instead, obviously it diminished in this form here, and we had the burst of the bubble just around the year 2000 or just after that. But currently still, traffic in networks is growing at about 30 to 40% per year, which is quite significant. So if we look at what that means, at 40% traffic growth per year, that means the traffic is going to double every 2 years. It's going to increase by a factor of 30x in 10 years, and by a factor of 1000x in 20 years. So to put that into perspective, if we were to think of ICT consuming currently about 2% of the world energy, and we were to do nothing, and provided the trends continue, then in 10 years we can expect that numbers to grow to maybe as high as 60%. Obviously that is not going to happen. And also there was this very significant challenge for people to try to reduce the energy use of communication networks and improve the ICT energy efficiency, especially for networks, by a factor of 1000. So if we're able to achieve that, then in 20 years we will be able to consume the same amount of energy as we do today, but accommodate the 1000 times increase. Excuse me for my voice. The 1000 times increase in traffic. Now, to understand what we can or should do about growth in traffic, we need to understand the trends and some of the strands of traffic. The smallest by volume is wireless voice, and this is not growing very large at all. The fastest growing is wireless data. Excuse me. The fastest growing is wireless data. The largest by volume is internet video, and the second largest is peer-to-peer. And this is the total backbone traffic, and this is in North America, traffic in terabit per second versus the time in years. And this is again from Bell Labs as part of Green Touch. And therefore, any kind of set of measures that tries to improve energy efficiency has got to address those three areas. And those standards in the core network and in the emissions address the first two, the internet video and peer-to-peer. And the hardware part is obviously applicable to all three areas. Just a little bit about the Green ICT initiative itself. IEEE introduces those initiatives continuously to ensure that IEEE remains at the forefront of technology all the time. So within IEEE there is a Future Directions Committee, FDC, and this committee looks at the things that are happening and projected to happen in the future, and therefore starts these initiatives to try to bring together all the activities within IEEE under one umbrella. And we have, as a result, the IEEE Green ICT Initiative, which started about 3 years ago. There are other initiatives. So there are initiatives in big data, in smart cities, and so on. The mission of the Green ICT Initiative is to bring those metrics, or to bring an increased awareness of green ICT, and to develop a holistic approach to sustainability throughout ICT by incorporating green metrics and design practices throughout the IEEE technical domains. Now, different work is done in different societies, Communication Society, Computer Society, Microwave Theory and Technique Society, and other societies. But the goal here is to try to bring them together so that green ICT and metrics derived from green ICT would become the norm when we come and design our systems. So the initiative is funded by IEEE, and it introduces new products and services within IEEE. So standards is one of them, and today we're talking about some of the standards activities, conferences, publications, and education. So within standards, there have been 9 standards proposals approved, and now we have the projects starting and hopefully running over the next 2 years to try to define them and finalize those standards I mentioned. In publications, there are magazines, a magazine proposal and a transaction, which actually started in January, and obviously courses and webinars. The goal is to try to have metrics throughout the IEEE that relate to hardware design, energy-aware algorithms, and hopefully for proportional computing included in the different areas within IEEE, but also within standards. So I'll start talking about the first area, standards for green core and content distribution networks and virtualization. The first standard is IEEE P1925.1, which is a standard for energy efficient dynamic line rate transmission system. The idea here is to develop a standard that specifies an energy efficient rate adaptive transmission system, which can be used to deploy mixed line rates. So this is work, and the first 5 standards that I'm going to go through is work that has been developed to a large extent within the Green Touch initiative. And this involved a number of companies. I mentioned already Nokia, we had Huawei, we had AT&T, we had Intel, we had France Telecom, and a number of other companies that contributed to this. And I co-chaired the Wired Core and Access Network Working Group there. And this is one of the areas that were developed there. So the motivation for this is that traffic varies during the day and at different points in time. And we have transponders and also routers that work at a given data rate. And therefore, imagine a situation in which the traffic is, say, 110 gigabit per second. And you have got transponders that work at 10 gigabit, 20 gigabit, 10 gigabit, 40 gigabit, 100 gigabit, and so on. And now to meet the traffic demand of 110 gigabit, you can end up using, say, 2 transponders of 100 gigabit and therefore waste a lot. Or maybe you can use one transponder at 100 gigabit and another transponder at 10 gigabit, and therefore try to match the traffic to the transponders you have, and therefore reduce wastage and save power consumption. And this is the idea behind this standard, trying to standardize this approach. So it introduces the architecture and mechanisms needed to enable the use of an optimal combination of line rates to accommodate the traffic while reducing power consumption. Obviously, the purpose is to improve energy efficiency, and this is applicable in high-capacity core, metropolitan, and access networks. So here is an example where we have got power consumption of different equipment. So power consumption of a router port at 40 gigabits per second is about 1 kilowatt. Transponders, 45 watt at 10 gigabit, 73 watts at 40 gigabit, and 135 watt at 100 gigabit. So if we were to imagine an example in which we have got a traffic of roughly, say, 110 gigabit, then we can use two of the 100 gigabit transponders, in which case we consume 270 watts, or we can use one of the 10 of the 100 gigabit and one of the 10 gigabit, in which case we meet the demand, but in this case we will consume 135 plus 45, that's 180 watts, which is much less than 270 watts. Therefore, there is an advantage in trying to have granularity in the data rates that you support, and to use an optimal combination of these data rates to improve your energy efficiency. This can be taken further if OFDM is used, or signal frequency division multiplexing, and the optical version of this, where we have got the ITU grid, which is 50 gigahertz, that can be subdivided into a number of subcarriers, and therefore we use an optimum number of these subcarriers to meet our demand. Here is an example of an OFDM transponder that has got serial to parallel conversion, modulation, inverse FFT, parallel to serial conversion, digital to analog conversion, an optical transmitter, and then the opposite at the receiver. And this is what it can do. So I'll quote some numbers here just by way of example. If we go for a very low order modulation format, then we do not require very high signal to noise ratio. Therefore, we can transmit for over very long distances, in this case here 2,000 kilometers. Obviously, this includes amplification on the way. And this is the power consumption. We can go to higher order modulation formats, in which case instead of 40 gigabit, we can achieve 120 gigabit. But we require high signal to noise ratios, and therefore our transmission range becomes smaller and we consume more power. And therefore, there is an optimum combination here of line rates that meets your demand. Also, as you change those line rates or you use a higher data rate transponder, it doesn't go as far and may consume higher power, and therefore we need to come up with the optimum combination. Here is an example where versus time of day we show the power consumption. And as you can see, first at the small hours of the day, 2 a.m., 4 and 6 and 8 a.m., the traffic is low and the power consumption generally in all of the approaches is low. At the later time of the day, the traffic is high and the power consumption is high. We have got here the 10 gigabit transponder, and if we were to use 10 gigabit transponders throughout, then at low traffic they are a good choice. At high traffic they are not such a good choice, and we can see that very clearly from here. For example, if I was to use 10 gigabit transponders, I will consume 450 watts instead of just using one 100 gigabit transponder, which will consume 135 watts. Followed by closely better is 100 gigabit transponder. Having granularity is good, so 40 gigabit transponder. And then the red curve here is mixed line rates, and these are two versions, the lowest ones, two versions of OFDM, one that is spectrum minimized, so uses spectrum in a very good way, and the second is power minimized. This here shows a similar kind of set of trends, but what is important here is that we can have some good savings and combinations of data rates that can result in the best outcome if we were to use mixed line rates. One key question is how large should an OFDM transponder power consumption be before it becomes as good or not better than mixed line rates. So here we have got the worst case, 100 gigabit has got no granularity at all or not as good, 40 gigabit transponder, the 10 gigabit, the mixed line rates, and here is an example of an OFDM transponder up to maybe about 400 watts that is good. As good as mixed line rates. And we can also get a lot of saving in spectrum while not sacrificing a lot of degradation in power consumption, as we saw over here. The difference between the spectrum minimized and the power minimized is not very large, but if you also were to head for reducing the number of subcarriers needed, you can reduce that a lot, or significantly, by about 35%. And therefore, this standard is about coming up with the optimum combination of line rates to use to minimize the power consumption for a given amount of traffic, but also trying to look at ways whereby you can reduce the amount of spectrum that you use. I'll move on to the next standard, which is 1926.1, which is a standard for a functional architecture of distributed energy efficient big data processing. So currently we're seeing a huge increase in data, and big data has got a number of properties. Volume is one of the important ones. We have got variety. It comes from so many different sources. It has got velocity. It changes very quickly. It has got veracity. It means a requirement for accuracy and validation of the data. But one key observation in big data is that data is not knowledge, and generally people are interested in the knowledge that is included in the data. And therefore, there is a potential to try to reduce the volume of the data by just extracting the knowledge that is embedded in that data and transmitting the knowledge instead of transmitting the data. And therefore, there is a question of where do you process to extract knowledge from data, how much do you process, and how do you optimize this overall approach in a way that is interoperable. And this is the topic of this standard. So the standard specifies a functional architecture that supports the energy efficient transmission and processing of large volumes of data, starting at the processing nodes close to the data source. So as far as possible, if you can process near the edge of the network and reduce the volume right from the start, you then can end up with significant savings in terms of power consumption. And then we can provide more processing resources in the centralized data centers. The purpose is obviously to improve energy efficiency of these big data networks, and the standard is needed so that these efforts can be coordinated all the way inside the data center, at the edge, and throughout the network. I'll just try to explain the principle here using two diagrams. So this is one example of a core network with a number of nodes, and here at the edge we have got different set of measurements. NHS is the National Health Service, which is like in the UK, the government entity looking at different hospitals and so on. Maybe financial data, social networks data, and maybe business data. Currently, all this data is taken in the network and is transmitted in a way that where we transmit all the information as big chunks, and we send it to central data centers for processing. Now, these big chunks going down the network will consume a lot of energy, and that is not needed because they actually represent data and not knowledge, and we're interested in the knowledge and not the data most of the time. So here is an example of distributed processing in big data, which is the goal behind this standard. We have got the entities that produce the data, and this may be in large chunks. Now, these chunks have had the opportunity to be processed in a small processing node here at the edge of the network. And that resulted in one of the chunks being converted into info, which is knowledge, not data. But this node was not large enough to actually process the other two chunks. So these other two chunks continue as chunks, and they come to this node here, where now here we have got enough processing capability to turn those two chunks into two further info, and therefore the info now proceeds all the way to the central data center. So we have reduced a little bit the traffic on this link, but we have reduced the traffic substantially on this link here. In this example, the traffic has been reduced all the way from the source into info all the way along, and therefore we get a significant amount of saving. Obviously, there are entities that own the data. There are data centers for processing, and the network operators may also own some of these nodes, and therefore there is a need for coordination in terms of how this process is done to process the data, but also to reduce power consumption in the network. I'll move on to 1927.1, and this is a standard for services provided by the energy efficient orchestration and management of virtualized distributed data centers interconnected by a virtualized network. What this standard is about is about providing computational resources and also networks that interconnect them in an energy efficient way, and also being able to share those computational resources and networks between a number of operators. So the general principle is that you will have a network that may be owned by a large operator, and then slices of these network may be provided to secondary operators or people who do not own the full infrastructure, but also want part of that infrastructure to interconnect their entities. And in addition, those secondary operators may be interested not only in network resources, but also in computational resources. So therefore, parts of the data centers may be sliced and provided to those secondary operators, so that they have computational resources and network resources that they do not necessarily own as physical entities, but have full access to, and these are protected in a virtual kind of setting. So the standard specifies an architecture for a service composed of distributed data centers interconnected by a network, and it specifies the interfaces and the dynamic orchestration and management mechanisms for this energy efficient allocation of resources from data centers and network. The purpose is obviously to provide energy efficient networking in this case, but also to enable this concept in the first place. And the need is to reduce the energy consumption of virtualized interconnected data centers. I'll try to show this here through an example. So here is a network, and these are three enterprises that request these different network topologies, or maybe three virtual network operators that request these different virtual network topologies. Each line here is a link that represents communication, and each node here is a set of servers or processing capability that this operator requires. So here is an example of how we try to meet that demand. We placed one node here, one node at this second node in the network, and the third here, and then we interconnect them. So the process of taking the virtual request into the physical network, we call that embedding. And then here is another example, and these have been embedded here, and this is the third example, and they have been embedded in this way. And as you can see from this example, there will be several ways in which you can meet those requirements, and therefore there is a need to find the optimal way of doing this in a way that minimizes power consumption. And this standard specifies the algorithms needed to minimize power consumption in this setting. So here is how it can be set up in an optical network, physical layer, and an IP layer running on top of that. And here are requests where, for example, we have the green request, somebody requesting a network of this topology. It has been embedded in these three nodes and interconnected. The blue requested this kind of topology, and it has been embedded here, here, and here, and they have been interconnected. And the yellow said, well, they are happy even if all their nodes are embedded in the same node, so they are embedded in here. And the orchestration and management of this is what this standard is about. P1928.1 is a standard for a mechanism for energy efficient virtual machine placement. So the purpose here is, now currently we do obviously a lot of the computational tasks that we have in virtual machines. And these virtual machines can be placed in different regions in our network. Now imagine a scenario in which we have a network that covers, say, continental US. And we have got a number of users in the East Coast, and these users in the East Coast request a virtual machine, and the virtual machine happens to be in a data center running in the West Coast. And therefore, we're going across the network from East Coast to West Coast to try to provide that virtual machine to the users who are located in the East Coast. What will be more efficient is to migrate that virtual machine closer to the users in the East Coast so that they do their processing locally if possible. Now, what happens then if we have got users in the East Coast and users also in the West Coast interested in this virtual machine? Where do we place it? What may be a good idea here is to replicate it. So make one copy in the East Coast and one copy in the West Coast. And then replication can be in two flavors. If you make a copy, it uses as much energy as the original copy, and we call that simply replication, or it may be in a way that if half the users use it, then it uses half the energy, and we call that slicing. And therefore, this standard here is a standard for a mechanism for energy-efficient virtual machine placement. Where do you place virtual machines in your network in a way that minimizes power consumption? So this standard specifies an algorithm for energy-efficient virtual machine placement, a set of strategies, considering network and computational power consumption. It also considers the geographic distribution of user demand, as I have just given in the example. So the purpose of this standard is to enable energy-efficient processing of information, and we have got data centers that are distributed across a range of geographic areas. So here is an example of a network, and this is a network that covers continental US with 14 nodes. We have got a number of users who are interested in a number of virtual machines. And the question is, where do we place those virtual machines? In other words, where do we have them placed? Where should we have clouds in this network? So the number of clouds and the location of clouds. And once we have done that, which virtual machine should be placed in which cloud? And then subsequently, we need to build those capabilities within those clouds, and therefore the number of servers, the number of switches, and the number of routers, which may already be embedded in these clouds, but we are just switching them on or bringing them online. And then finally, we need to find the best routes to take the information from the virtual machines to the users in a way that minimizes power consumption. And therefore, and these are the kind of savings in power consumption that we get through those approaches to slicing, which is an approach in which you can make copies of the virtual machine where each copy consumes just an amount of power that is proportional to the number of users that are using it. Currently, we do not have that, at least not implemented widely, and therefore in a later standard that I'm going to talk about, you will see ways in which we can introduce power proportional computing. If we do not have power proportional computing, then we can either migrate or replicate. But if we can do slicing, we can achieve a lot more energy efficiency. I have already mentioned the migration, the replication, and the slicing. Migrating means move the virtual machine closer to where the users who are using it are. Replicating means make a copy next to each cluster or group of users. Slicing means make a copy next to each group of users, but each slice uses a smaller amount of power proportional to the number of users. And there is a heuristic or an algorithm for doing this. And as you can see here, these are node IDs of the network, and these are the number of virtual machines placed. Under slicing, you make a copy almost everywhere. Under replication and migration, you make copies in very popular nodes. And here, node 6 is a very good node. It's equidistant or has got the minimum average hop distance to every other node in the network, and therefore is a good placement. I'll move on to talk about 1929.1, which is an architecture framework for energy-efficient content distribution. So in a similar way that we have to place virtual machines in an optimum way, also content has got to be placed in a good position. Currently, about 90% of the traffic, about 90% of the traffic on the network is a form of video, and therefore if we're able to reduce the power consumption associated with video distribution, then we can reduce the power consumption quite significantly of networks. And we can do this through content caching or making copies of the content closer to users. And although this has been kind of examined for reducing latency, it has not been examined for, at least not standardized, for reducing power consumption. And the purpose of this standard is to enable this for reduction in power consumption when we consider content distribution. So again, here is a network with a number of users who are interested in content. The question is, where should we place this content? And then how many clouds should we we have, or where should they be placed, and how to route the content optimally from these clouds to the users in a way that minimizes power consumption. Now, the obvious question may come to your mind: if you're making copies of content everywhere, are you not increasing actually power consumption? And it turns out that we can actually reduce power consumption. The main reason for that is that content popularity usually has got a distribution like this, which is a heavy tail distribution. If you look at the likes of YouTube, for example, while it may have few hundred million maybe videos, only maybe 50 or 100 videos are the most popular ones, and they account for maybe 70 or 80% of the hits on the server. And therefore, you do not need to make a copy of everything. You only need to make a copy of these most popular content and replicate them in the different locations in the network. And by doing this, you will have, yes, increased the power consumption of some of the nodes, but you have significantly reduced the journeys up and down the network to get the content, say, from a centralized node. Doing this, the sort of power consumption savings, the maximum that we can get in this example here is about 70%. And these diagrams here show how we are replicating content. So I'll not go a lot through that, but a dark dot means that content is being replicated. Here we have popularity groups, 50 popularity groups, and along here we have got the network nodes, which are 14 nodes. And at 6 a.m., for example, there isn't a lot of traffic, and therefore we are only putting, or we're putting all the content in a central node, which is node 6 in this case. At 10 p.m., the traffic is maximum. The most unpopular content is still left in the central server. The more popular content is replicated everywhere. And therefore, the decision to replicate is dictated by two things. One, the popularity of the content. If content is not popular, you're always going to place it or leave it in the central server. Second, by the amount of traffic that you have in the network. If everybody is sleeping, there is no point, or if everybody is not accessing content, there is no point in replicating content. Only when the traffic is high, replicate the content. And the standard tries to organize the way that content should be handled in a way that is energy efficient. I'll just mention one or two things about Green Touch, which worked between 2010 and 2015. To reduce the power consumption by a factor of 1,000. The core network and the content distribution network had a goal of roughly about 300. And here is an example, another example of a continental US network. And the power consumption in the end was reduced by a factor of 1,000, and this was done, and the methods needed to achieve this were shown year before, end of 2015. And these are projections of traffic using the methods and power consumption using the methods introduced by Green Touch. Currently, networks do not adapt. They consume the same amount of power, whether the equipment is handling a lot of traffic or little traffic. Here with Green Touch, it adapts with the kind of traffic that we have, and in the end, the energy efficiency is improved by a factor of 316x. This is for the core network. Overall, it is 1,000x. What this was made up of is some business as usual, more so improvement. Some improvements in hardware, interconnects, and optimized packet processing, link optimized signal processing in transponders, protection resources that were usually left on all the time, so here are turned off, router bypass and sleep modes, dynamic allocation of line rates, optimizing the network topology, and optimizing the cloud and virtualization. And this gave the overall factor, but also, as you can see here, the standards address a number of these areas. For example, the content distribution, the mixed line rates, and because we're doing the routing, therefore some of these sleep modes and so on, and some of the link optimization methods. But in addition, introduce a number of other areas for other standards that are not directly related to the work that was done in Green Touch. So I'll start talking now about standards for energy efficient communication hardware. So this standard P1923.1 is a standard for computation of energy efficient upper bound for apparatus processing communication signal waveforms. What this means is that generally there are a number of different modulation and coding techniques, different signal waveforms that we can use with our different communication systems, and these result in different energy efficiencies. And the standard is about identifying a way to measure the energy efficiency of different signal waveforms given certain types of power amplifiers that may be used. And while the first set of kind of standards I talked about were more relevant to communication society, computer society, and so on, this is a contribution that was made to the Green ICT Initiative by the Microwave Theory and Techniques Society. The method enables us to evaluate the energy efficiency of these different waveforms. Also, it allows us to design or to look at the optimum or the best kind of waveforms to use to establish the best energy efficiency if the hardware is fixed. So you can look at it both ways. The waveform is already pre-selected, what kind of energy efficiency will it give, or the hardware is known, and we can look at the best kind of signal waveform that we can use to provide or to produce the best energy efficiencies. And obviously this is relevant to different wired and wireless communication suppliers and operators. Okay, so this diagram here shows the best efficiency that we get for power amplifiers, and these here are different modulation techniques. And as we go here to the right, this is actually also time progressing. So these are the more recent kind of approaches. So linear power amplifier efficiency is dropping, as you can see in here, with newer standardized signals. Signal modulation selection places this efficiency ceiling on the transmitter design, and therefore we need to be able to predict this power amplifier efficiency ceiling first at the time we do the standardization before the signal design, and also using a uniform and consistent methodology. And what this is what the standard tries to achieve, as I have mentioned. So here is a little bit more detail. If you look at the power consumption or the power that comes from the source, there is a certain DC amount of power that is drawn. There is a certain amount of input power that is input to the amplifier, and this is the input signal power. And then the good power is the power that is produced at the output as radiated, for example, RF power. The rest of the power here is dissipated. And therefore, the goal is to try to minimize this power dissipation and to maximize this signal power that is radiated as useful power. This is the power supply, and this is the heat sink size. So the lower efficiency is usually driven by signal modulation. So for example, if we have a large number of zero crossings, that can lead to lower efficiency. A large heat sink can end up being required to absorb the dissipated power, and we may also need a large amount of supply for a given output RF power that we need. The goal is to be above 45% efficiency, and generally above 70% it is diminishing returns. And therefore the standard is about finding the optimum way to design or select signal waveforms for a given circuit design, but also to be able to assess if that design is fixed, what can we achieve with a given signal waveform. I'll move on to talk about P1924.1, which is a recommended practice for developing energy-efficient power proportional digital architecture. I mentioned earlier on that virtual machines and computers and so on currently consume a large amount of power even when they are idle, when they are not doing any work. And the goal of this standard is to find or to identify a set of guidelines for designers and developers of digital architectures that ensure that power is only consumed when useful computational work is done. And the need for this is obviously to reduce the power consumption of devices when they are in idle mode, and also to only consume power when we are in the on state doing useful work. And therefore, we need to go to an on, but also we need to be operating at logic switching speeds. This is very important for digital hardware designers, for system architects and chip manufacturers. Now, in digital hardware, there is no output power here because everything is just about processing, so bits in and bits out. And therefore, by definition, the energy efficiency of any digital processor is inherently zero, since we are not producing any output power. And therefore, the goal is to actually minimize this power dissipation here. And if we look at this in a kind of an example, this is the computing activity, and this is the power consumption. The current hardware we have consumes power even when there is no computing activity being carried out, and then has got different slopes. Some of them are very flat. This is not very flat, but some hardware has got almost flat power consumption versus computing activity. Ideally, we want to get to this kind of shape here, and in which case we consume zero power when there is zero computing, and then we have got more power consumption as the computing activity increases. And this is the amount of power that is saved. So we obviously must not impact the processing throughput. We should also make sure that energy drops with activity or with the duty cycle. Ideally, we should go to zero with no activity, like we're showing here. And there are a number of methods that are used in this recommendation. Lower input energy and lower cooling requirements. And the applications are in many areas, in energy harvesting applications, in battery powered applications, and in data center applications. Okay, so the last set of standards are standards for ICT emission estimation. So the first of these is P1922.1, which is a standard for a method for calculating anticipated emissions caused by virtual machine migration and placement. So the idea here is that suppose you were to think about some of the examples I gave earlier on, where virtual machines were moved to different locations. Now what we can do also is we can move virtual machines to locations where we know that the energy is clean energy, and therefore we migrate it to where energy is generated, say, from renewable energy or hydro energy or some form like that. And therefore this standard is a method for calculating the anticipated emissions that may be caused by virtual machine migration and placement. So the purpose is to assess the anticipated emissions caused by this virtual machine migration, and we are interested more, or the standard is more interested in marginal emissions. Now what we mean by marginal emissions is that a certain region may be known already to have clean energy, say in Ontario, say in Canada, Ontario for example. Another region may be known to have generally emissions, high emissions, means the energy comes, say, from oil or something like that, like in Canada, for example, Alberta. But that cannot be used all the time to mean that it is good to place virtual machines in Ontario and not in Alberta. What matters is at the point when we're placing the virtual machine, what does the energy supply mix look like, or the extra power that we use, is it coming from a clean energy source or not? And therefore we need to be able to measure that extra emission to make correct decisions about the placement of virtual machines. So here is an example where data centers can be placed in or are in different locations in the country, and we can place the virtual machines in any of those, and we are interested in minimizing the marginal greenhouse gas emissions, the extra emissions as a result of placing the virtual machine in a given location. And we have here an Ontario example and maybe an Alberta example, which will become clearer here. So here we have the time of day versus the amount of greenhouse gas emissions And in general, Ontario is the red curve here is lower, so greener in terms of emissions, and Alberta is not as green. It comes from oil, a lot of it. Now, if we were to look at a given point in time, then the decision may be reversed. So, for example, at this point in time here, as it happens, Ontario is producing, or the amount of emissions there are higher than Alberta, simply because of the kind of energy mix that is being used at that point in time. And therefore, it may be better not to migrate machines from Alberta to Ontario at this point in time. Now, here is the emissions between 2011 and 2013, by way of example. This is for just servers placed in Alberta, the blue, servers placed in Ontario. And obviously, Alberta is much higher than Ontario. But if we were able to migrate and place them optimally, then we get this green curve here. And that means we can save as much as 44% emission compared to just placing things in Alberta all the time, 9% of the emissions compared to if we were to place them in Ontario. Okay, P1922.2 is a standard for a method to calculate near real-time emissions of information and communication technology. So the previous one was about the marginal emissions and where to place the virtual machines. Now here we are interested in the keyword here is real-time or near real-time. That means currently a lot of the emissions are estimated based on the average fuel mix or the average emission in a country or a region. We want, or this standard here looks at introducing real-time capability to make the correct decision at a given point in time, not using just the history of the previous year and what happened over that time. So the purpose of this standard is to enable near real-time assessment of ICT infrastructure use phase emissions by taking into account the temporal variations of emissions relating to electricity generation. So here is an example of the power mix that is used in a given region, here in this case Ontario. So a large amount is produced, so this is time of day and this is the amount of power in megawatt. A large part comes from nuclear. Then we have got wind and other are quite small here, so not very clear. Hydro is this part here, the natural gas, and the coal is this section. And the dotted curve here is the emissions, which are read on the right-hand axis. And generally, people have used in the past a straight line like this, almost an average amount of emission for the region, whereas the real-time emission may look like this red curve here that goes up and down, and therefore there can be quite a range of errors if we were to just use the average value at any given point in time. So here is the power consumption required by ICT in this region, say Ontario. And here is the historic kind of mix, so nuclear 59%, coal 2%, etc. And if we were to use these to estimate the emission of the ICT in this region, it will be 241 tons of CO2 equivalent per year. If we were to use the actual real-time measurements, then we end up with a 265 tons CO2 equivalent per year, which means that just using the average values, we underestimated our emissions by a factor of about 10%. And therefore, this standard is about standardizing and also bringing real-time capability to the measurement of the emissions. Okay, so I have talked about the 9 standards that have been introduced. Just briefly 2 points before we start taking questions. Next steps. So this is a call for participation, and the call has been issued for a number of these standards already, and others will have a call issued during March of this year. The expected date of submission of drafts of these proposals to IEEE-SA for initial sponsored ballot is between July and September 2018, and we expect the project's completion sometime August to September 2019. The range in dates is because for different standards there is just different dates specified. So please join and participate. And also we try to include a range of references for people who are interested in knowing a bit more. So I'll stop here and I will open the floor for discussion and questions. Okay.
Hi, Jafar, can you hear me?
Yes, I can. Thank you.
Sorry, this is David. I did get a couple of questions here. I think they're more geared towards you than our guest speaker. So if it's okay with you, I'll read them aloud in the order in which we received them.
Okay.
First question came through from Atul Tambi. Excuse me if I'm mispronouncing your name. Question asks, I believe that mega data centers from companies like Google and Facebook may be consuming a lot of power and may have been doing so some time to go more green. What is the IEEE doing to get those companies involved and get their practices more widespread, if anything? Can you answer that?
Yes, I think I got the gist of the question. These companies obviously have got huge data centers and they consume a lot of power. They have also been good in that they have improved their PUE, the power usage effectiveness, which is the kind of the ratio of the total power that is taken from the supply as compared to the power that is used by the ICT equipment within the data center. At one point, PUE numbers were as high as 1.5, means you take 1.5 times the actual power that you need to operate your service and communication. Now numbers are getting down to 1.1 or maybe less than that. And therefore credit to these companies. IEEE is getting involved or is working with a number of these. Some of them contributed already to Green Touch and hence are now contributing to the initiative, but also hopefully through these standards we will have involvement more with the companies that are interested. As you can see, a number of these standards are geared towards reducing the power consumption by looking at optimum ways in which things can be done in these data centers, but also in the network. So please, if there are activities and interests, please get in touch with us.
Okay, thanks, Jafar. We had another question come through. This one comes through from Sandy Rotter. Sandy, thank you for your question. Jafar, are you including tragedy of the Commons electromagnetic compatibility spectrum sustainability metrics?
The focus here mainly is on energy efficiency. I'm not so sure I follow the question in total, but at different points we included other metrics in addition to energy efficiency when trying to optimize the network. So we included spectrum, for example, spectrum efficiency as one of our kind of metrics. We included coverage, especially for wireless, as another part of the metrics. Electromagnetic contamination, although is not part of the standard here directly, but also in form of interference and so on. There have been studies looking at minimizing those, although the standards here focus more on just energy efficiency. I don't know if Earl is online or would like to say a little bit more.
Okay. Yeah, the analysis so far, as Jafar said, has been looking at the power consumption of the thing. We have not yet looked at the electromagnetics, though that's something that I would be very happy to get into, being one of the hardware people here and a representative of NTT. So well familiar with that, but no, that's not part of the discussion yet that I'm aware of.
Thanks, Al. And maybe it is a point for us to connect with the question and engage with people interested in this more.
Okay, Jafar, we have another question that came through from Victor D. Pasquale. Victor, thanks for your question. You described logical network topologies. In the standardization process, what depth of commitment to physical networking technology is being made? Can standardization research proceed at a purely logical level?
It's a very good question. There has been quite a detailed involvement with the hardware because ultimately, as we know, power is dissipated in the real hardware, and therefore a lot of the work in terms of so the two examples of the hardware that I gave earlier on in terms of signal waveforms and also in terms of power proportional computing, look at the specifics of the hardware and improving energy efficiency there. The standard that I mentioned on mixed line rates and so on looks at the details of the hardware and trying to improve things there. I did not mention more specific ones relating to, for example, routers processing, speeding, and slowing down the processing speed within the router according to the type of packets or size of packets that are being processed. So when you have very short packets, then the header is a large part of it and you need to work a lot faster. So this kind of adaptive rate in terms of processing, so working with the hardware at that level. And then also the improving the DSP in transponders. So these are areas that will feed into elements within those standards. So they're not totally at the logical level. I went through that slide a little bit quickly, but maybe we can just show quickly the slide that I meant with some of the green touch. There's also, there are these elements on signal processing and transponders, the optimized packet processing, the interconnects, and the interconnects were in the transponder, and the allocation of the line rates, and obviously two standards relating directly to hardware, these 1923.1 and 1924.1. So I hope that it gives you an idea of some of the hardware elements, but if there is also interest in emphasizing some of these more engagement with us in these standards will be great.
Okay, Jafar, we are near the end of the presentation. I did get one more question, so we'll take this last one from Mark Schaefer. Thanks, Mark, for your question. And I think it speaks sort of to your last point, Jafar, about calls for participation. Who has signed up so far for these working groups for these standards? And then two-part question, what is the timeline for producing the standard?
Okay, so we have had a number of people from different societies, from the Communication Society, from Microtheory Techniques, from Computer Society, and Nuclear Technology Society, so different participants. The Green ICT Initiative has got a very large membership, but the ones that have signed are from these societies, and they are into the lower kind of tens order. But obviously this is a call for more people to get involved and engaged. In terms of the timeline, for some of them, I mentioned a call has already been issued, and usually after the call, we allow about 1 month to hold our first meeting. So there will be meetings starting to be scheduled from March and April and so on. The timeline, I mentioned that briefly. So July to September 2018, we're supposed to have a kind of a draft. And then there is roughly about 1 year after that for the final approval and ballot. And I think there is a slide here with the timeline, which hopefully will show this. Thank you.
Okay, Jafar, can you hear me?
Yes, I can.
Great. Thank you so much. We are a little bit over, so I want to be respectful of everybody's time. Thank you, everybody, for joining us. Thank you, Jafar, for your guest appearance today and your presentation. We are going to, again, share out the recording from today's presentation. The IEEE Standards Association will let everybody know who participated today where to find that. And with that, I will end today's session. Thanks for joining, everybody, and have a great day.